Hi, my name's David and I'm a kernel hacker on the Open Kernel Labs team. Today I'm here to talk about scheduling in the OKL4 kernel. I guess the first question is, what is scheduling? It's quite easy. In a system, we might have multiple threads ready to run at a particular point in time. It's the scheduler's job to work out which thread actually should run next. In the OKL4 kernel, we use something called strict scheduling. So for instance, if we've got 3 threads ready to run, the OKL4 kernel will always choose the highest priority. So in a mobile phone, for instance, your high priority thread might be the radio communications module, while low priority thread might be the user interface. Or in a car, for instance, your high priority thread may be the ABS braking system in the car, while your low priority thread might be your MP3 player decoding, and your song say. Now, OKL4 will always choose the highest priority thread ready to run, regardless of how much time the thread's already had. So, if your ABS system decides that it wants to take up 100% of the CPU, the lower priority threads will be starved. But as much as like Enya, I'm probably happy that my ABS system is getting the CPU time. Now, one problem that we hit in strict scheduling is a well-known problem actually known as priority inversion. And this occurs in the following sequence of steps. If your low priority thread acquires a lock or mutex, which would represent like this, it may then be preempted by higher priority threads as they become ready to run. If at a later point in time though, a high priority thread attempts to acquire the same mutex, it will no longer be able to continue because the low priority thread already has it. The scheduler will no longer consider it. This presents a problem though, because now a medium priority thread is just going to continue running, never giving the low priority thread a chance to release the mutex. And this is called priority inversion and is a serious bug. In OKL4 version 2, we solved this problem by introducing something called schedule inheritance, or priority inheritance as it is better known. What will actually happen is if a high priority thread becomes blocked waiting on a low priority thread, the low priority thread will inherit the high priority thread priority, and therefore it will be chosen over this other middle priority thread so that the blocked thread may continue to run in the future. And this is called priority inheritance. Let's have a look at a more complex example over here. Now, in this situation, we have 4 threads. The high priority thread is attempting to acquire a mutex held by a thread of priority 2. This thread in turn is attempting to receive an IPC from a thread of priority 3. But this thread in turn is also trying to send an IPC to a low priority thread. What OKL4 will actually do is propagate the priority 4 thread's priority through this chain of dependencies down to the low priority thread, and hence you won't have this priority inversion problem. Now just a couple of notes about our implementation. OKL4 does not approximate the priority inheritance protocol as some other products do. We always have the correct priorities calculated at every point in time, and we still manage to do this with our order 1 scheduler and having blazingly fast IPC. So how can we do this? Well, it's top secret, sorry. Wait, no. You can download the source code on our website. Check it out.